Hello learners, I am Dr. Anuj Kumar Sharma. I am working in Center for Advanced Studies as an assistant professor in mechatronics department. So, today we will discuss the strength of material. So, it has 5 units, but we will discuss the first unit of this subject. It is simple stress and strain. Basically, it has different types of stresses, different types of strains, and we will discuss how these stresses behaves in our daily life and how they impact the material. So, as far as the subject name is concerned, it is strength of material, but we are not going to calculate the strength of material. We generally measure the stresses which are induced in the material with the application of forces. So, this is the outline of my lecture. So, here we will proceed like this. First we will calculate the direct stress and types, then shear stress, then normal stresses, then shear strain and various elastic constants. So, these constants are very important because we have to determine the length elongations in various rods. So, there these elastic constants are very important. So, as we know strength of the material. So, already I have told you that we are not going to calculate the strength of material, but we generally calculate the stress. So, what is the strength of material? So, basically it is the maximum resistance offered by any material to the externally applied force or load. So, when we applied any force on any object, so generally it induces the different types of resistance forces in it. So, these resistance forces try to resist the deformation which are to be caused by the application of external forces. So, it is very simple, we can also explain what is load. So, load is basically the external forces which act on a rigid body. So, these are known as the loads. So, generally we can classify these loads in different categories. First is the tensile load, second one is the compressive load, and third one is the shear load or shear force. So, as we can see the tensile load or tensile force and compressive force, these two forces are known as the direct forces. Why these two are known as the direct forces? Because we can see from the diagram, here we have a body that is shown in the green color. So, here we can see that these forces are being applied. So, these are tensile in nature. Why tensile in nature? Because they are trying to pull the object, they are trying to elongate the object, they are trying to increase the length of the object. So, to resist, so these are the forces, they are trying to increase the length of the object. This is the second case where the compressive forces are being applied, where their main intention is to reduce the size of the object. So, these are direct forces. Why direct forces? Because here we can see these are acting perpendicular to the cross sectional area, and in the second case they are acting in this direction. So, they are compressing the object. And third one, here it is the shear force. So, these forces acts parallel to the surface on which these are applied. So, parallel to the forces surfaces means let this is the surface and the forces are being applied on this object parallel to the surface. So, they create shear stresses. So, that is why these forces are known as the shear force. So, we will start with this normal stress and normal strain. So, what are the stresses? Stresses are basically they are little bit different than the pressure. So, what are the stresses? So, whenever we apply some forces, let us say we are taking this example, here this is the body and we are applying F Newton of force at this particular end, F Newton of force at this end, and this is tensile in nature. So, it is trying to elongate the object length, and because of these forces, so this body in itself is generating some resistance force. So, these forces which are shown in the red color are the resisting forces. So, on the right side we can see the area of the object, cross sectional area of the object. So, these forces are being applied perpendicular to the area. So, that is why these are known as the direct forces, and because of these actions they are trying to stretch this object and this object is resisting the external forces. So, these forces are trying to resist the elongation in the object. So, these stresses are known as the direct stresses or simple stresses. So, we can see it is generally represented by sigma, it is the symbol by which generally the stresses are shown. So, mathematically if you want to define it, it can be defined as internal resistance force. So, this red color, this is the internal resistance force, this blue color, this is the externally applied force. So, when we divide externally applied force by the area, so it will give us the pressure, external pressure. When we divide this F, this is the internal resisting force, divided by the cross sectional area, it gives us the stress. So, this is the basic difference between stress and pressure. So, mathematically these are same. So, if we are trying to establish the equilibrium, or we can say the body is strong enough or it is rigid enough, so it generates the same amount of stresses which the external force is applying pressure on the object. So, it means that is why we are able to see here we are applying F force and here we are getting the F internal resistance force. So, this internal resistance force divided by area will give you the stress. So, the unit of this, if we calculate the unit of this stress, so it is equal to internal resistance force, the unit of this is Newton and the unit of the area is, let us say it is meter square. So, we can say Newton per meter square is the unit. So, this Newton per meter square is the Pascal SI unit of this stress, and generally it is represented in the terms of Newton per millimeter square. So, generally we represent, because as far as engineering branch is concerned, we generally measure the dimensions in millimeter rather than measuring in meters. So, this is the direct stress or simple stress. So, generally we can classify the stresses into different categories. So, as far as the type of loading or type of application is concerned, we generally classify it into two categories. First is the normal stress, second is the shear stress. So, normal means, I have already told that normal means whenever we are applying force perpendicular to the area, let us say this is area and this is the force. So, perpendicular to the area means normal, and if it is parallel to the surface then it is shear force. So, two types of stress is normal stress and shear stress. So, normal stress further can be classified depending upon the type of force. So, if it is compressive then compressive stress, if it is tensile then tensile stress. So, we can understand with the help of these two diagrams. So, first one is we are applying the tensile force. So, these type of stresses which are being induced due to the tensile force, these stresses are tensile stresses. So, tensile stresses means we can see the force has tendency to elongate the body, therefore, the tensile stresses try to resist the elongation in the object. So, tensile stresses means what is the nature of tensile force? Tensile force always try to elongate the object. So, the tensile stresses what they do? They try to keep the original size of the object. So, if external force is trying to elongate it, so they will try to compress, means they will try to compress it to keep it in the original shape. And when we are getting the external compressive force like in the second case, so these two forces are trying to compress this object. So, it means it will induce the internal resistance force which will try to keep this the size of this object in its original dimension. Therefore, these stresses are compressive stresses. So, and the another one is shear stress. So, we will discuss shear stress in the next slide. So, we can understand that whenever forces are normal to the surfaces, they are direct stresses. Whenever the force is acting parallel to the surfaces or internal resistance offered by the object is in direction parallel to the surface, then it is known as the shear stress. So, here we can easily understand with the help of this example. So, let us say this is the cuboid where these forces are being applied parallel to the surface. So, this is the surface and this force is being applied here, but if we are applying some force in this direction. So, what this force will do? It will try to keep this object moving in this direction along with it. So, it means we have to resist that motion. So, here we can see the same amount of force we are applying in the reverse direction, or just what we have done, we have just grounded this surface, so that the stresses should be induced in this body. So, what they will do? They will try to generate the stresses. So, here let us say if we imagine this object is being made up of different layers. So, this force is being applied on the top layer and this force on the bottom most layer. So, these two forces together will try to shear off the different planes of the object. So, here we can see when equal and opposite forces act parallel to the surface on any cross sectional plane of the body and has tendency to slide its one part over the another part, then the induced stresses are known as the shear stresses. So, shearing means sliding of the individual planes over another planes. So, by the formula, if mathematically we want to see, it is generally represented by tau. So, tau is equal to shear resistance force, means this is the force which we are applying and the force which would be generated by this object inside it, that is the resisting force. So, that resisting force is always equal to this force. So, F. So, that is the resisting force divided by the parallel area. Here we are not considering the normal area, here it is parallel area. So, the unit is already same as in the previous case, force, this is also Newton and this is area meter square. So, it means this is the SI unit of this shear stress. Now, let us come to the strain. So, strain is also dependent on the stress, and here we can see in the previous case what we did, what we see, the body try to generate the same amount of force which we externally apply. So, in that case there is no any deformation, but let us say if we are trying to apply more force and the body is not capable of applying the same amount of force, then what will happen to the object? The body will get deformed. So, here we can see, let us say we are applying this much of intensity of force externally, it is tensile in nature and body is capable of applying only small force as compared to the externally applied force. Then what will happen to the object? So, this force will not be compensated by the internally developed resistance force, then the as a result what will happen to the object? This body will get elongated. Let us say from this example, initially the length was L and upon the application of this external force, so we could generate only F minus dF force. So, because of this difference what had happened to the object? Its length has been increased by dl. So, it means there is some elongation. So, this kind of deformations are measured in the form of strain. So, strain is what? When external forces are applied on any body and the body cannot offer sufficient resistance force to oppose the externally applied force, then some deformation is produced in the body. So, this deformation, whatever deformation, here in this case it is delta L. So, this deformation per unit original size of the object, let us say original size was what? For this case it was L meter and now the elongation is how much? It is delta L, means final length minus initial length, how much it is? It is delta L. So, the strain would be, strain is generally represented by epsilon. So, epsilon is equal to change in dimension, means here it is how much? Delta L, and what is the original dimension? It is L. So, delta L upon L, this is the strain. So, we can see here also it is, let us say it is measured in form of meter and length is also measured in form meter. So, it is cancelled out. So, it means it does not have any kind of unit. So, it is dimensionless quantity, right. Now, how many types of strains? So, strain means, as we understood that strain is caused due to the stress developed in the object, and we can see from here the strain as similar to the stresses can also be categorized in different categories. So, here we can classify it into two types of category. First is the normal strain and second is the shear strain. So, whenever force is applied parallel to the surface, then we will get shear strain, and if it is applied perpendicular to the surface, then it is known as the normal strain. So, normal strain also dependent on the type of forces which we are applying. So, if force is tensile in nature, here we can see it will create the elongation. So, it means it is tensile strain. So, the length of the object would be increased and it will create some elongation in the direction of the object. So, here we can see epsilon linear, or we can say the tensile strain is equal to increase in length, that is also delta L, upon original length, that was initially L. So, here we can see the tensile strain is equal to delta L upon L. So, it is positive strain because dimension is being increased. Here in case of compressive strain, when we will see this is the body and initially it was of L length, we compressed it, we applied some compressive force. So, what had happened to this object? So, some reduction in the length of the object happened. So, it was the length of the object was reduced by delta L. So, what is the decrease in length? This is minus delta L. So, it means it is negative strain. So, strain is equal to minus delta L upon L. So, this is the negative strain. So, here tensile strain is positive, it is negative. Now, we can see the shear strains. Now, shear strains. So, as we can see in the previous case also, so there was an object and we are applying some force parallel to the surface. So, some stresses were induced parallel to the surfaces, they were trying to deform the object, but in the previous case when the internal resistance force and externally applied force was same. So, it was not possible to create the deformation, but when the internal forces or resistance offered by the object is little bit smaller than the external applied force, then what had happened? Some strain were generated in the object and some deformation were created. Here we can see, so this is the object, this is the isometric view of this cuboid. If we will see this cuboid from the front side, so we would be able to see only this plane. So, we can see only this plane. So, we have grounded this object so as to create some stresses. So, here we can see initially let us say this body was here A, B, C and D. So, initially the object was straight. So, when we applied some force, let us say F force was applied. So, what had happened to this plane? So, this plane, so this D point was shifted to D dash, this C point was shifted to C dash and some deformation happened to this object. So, that deformation if we measure in the form of angle, so that has come phi angle. So, this deformation was happened. So, this is the deformation shear. So, when equal and opposite forces act parallel to the surfaces on in cross sectional. So, we grounded this. If we could not have grounded this object, then we must have applied this much of force, the same amount of force in the opposite direction. So, for compensating this force, what we did? We grounded this object. So, from this rectangle, if we want to determine the value of the strain or shear strain, then we can use this formula. So, this epsilon s means shear strain is equal to. So, if we consider this triangle or this triangle. So, if we apply the 10 rule to this triangle, so this is delta L deformation and this is, so if you want to calculate, this is right angle triangle, this is right angle triangle. So, if you will apply the tan phi, so tan phi is equal to perpendicular upon base. So, perpendicular is how much? Delta L, or we can say C C dash, this is the perpendicular upon base, base is how much? B C. So, C C dash is equal to, it is equal to tan phi. So, for very small value of this phi, so tan phi becomes phi almost equal to the angle. So, it means we can say this tan phi for very small value, for very small value of phi, tan phi is similar to phi radian. So, phi is equal to how much? C C dash upon B C. So, this is the shear strain. So, this way we can calculate the shear strain. Now, the next important term is volumetric strain. So, strain, if we want to define strain, strain is what? It is the deformation in any dimension divided by that original of that dimension. If we talk about length, then we have to delta L upon L. If we talk about d, change in diameter, then it is delta d by d. If we talk about the volumetric strain, it means change in volume upon original volume. Let us say we have one balloon, and initially let us say the size of the balloon is this much, and we compress it. Let us say initial volume is V, and if we compress it, so what will happen to its volume? Let us say we compress the air. So, then let us say it becomes V minus dV, change in volume. So, change in volume is what? It is dV. So, if we want to calculate the volumetric strain, then we can also calculate, it would be final volume minus initial volume upon original volume, or change in volume upon original volume. So, change in volume is how much? Delta V or dV, and divided by what is the original volume? V. So, volumetric strain is change in volume upon original volume. So, it is also the dimensionless quantity. So, it means if we want to calculate the deformation of any object, so we can calculate by calculating the change in the quantity by the application of forces divided by the original quantity. Now, these elastic constants are very important. If we want to understand the behavior of the material under different conditions of loading, then we have to understand various elastic constants. So, elastic constants are what? Constants means they are dependent on the type of material, they do not depend on the size of the object. Let us say if we talk about the steel, so steel has certain values of elastic constants, and they do not vary for different sizes, for different shapes. If we talk about steel, so steel plate, steel rod, steel circle, steel sphere, all these shapes will have the same value for modulus of elasticity. So, it does not depend upon the shape size. So, these are very important. So, before discussing the various elastic constants, let us have small discussion on the Hooke's law. What is Hooke's law? So, Hooke's law means within elastic limit, when we stretch something, so what happened to the object? We apply some force, it is stretched, when we release the force, it comes back to the original position. So, within that range, if we stretch it, then it comes back to the original position, it is the elastic limit. So, within elastic limit, if stress is directly proportional to strain, then we can say it obeys the Hooke's law. So, Hooke's law, according to the Hooke's law, we can have stress means sigma upon strain epsilon is equal to a constant. For elastic, for tensile loading, it is equal to E. So, this is the Hooke's law. So, modulus of elasticity means when we stretch something, let us say this is the object and we stretch it by applying some pressure or some force, and let us say delta L upon L, it is the strain. So, according to the Hooke's law, E is equal to normal stress upon normal strain. So, E, this is the modulus of elasticity, and this represents the speed of elasticity, means ki as fast as the material can get its original shape upon the removal of the load. So, as soon as we remove the load, it comes back quickly to the original position. So, in case of rubber and steel, when we will compare these two, so steel has more elasticity as compared to the rubber, because when we compress the rubber, it takes some time to come to the original position, but when we compress the steel ball, then it takes very small time to come back to the original position. So, modulus of rigidity, so this is also the elastic constant, it represents the rigidity of the object, how rigid the object is. Rigidity means whenever we apply some force, it very difficult to get deformed, then this kind of object is known as the rigid object. So, if G is high, then the object would be more rigid, okay. G is low, object would be less rigid. So, it is generally represented by G. So, shear stress upon shear strain, the ratio of shear stress to the shear strain, that is known as the shear modulus or modulus of rigidity. Next is bulk modulus. Bulk modulus means, let us say we have this object and we are applying some forces. So, whenever we apply some force on this object in this direction, so it will create some stresses in this direction. Let us say this is tensile force, tensile stresses would be induced, but simultaneously the cross sectional dimensions of this body will also be reduced. One dimension would be increased, other two dimension would be reduced. So, simultaneously it will have so many stresses induced on the object. So, let us say this is the 3 dimensional object and we have sigma x, sigma y, sigma z, 3 stresses induced in 3 directions. So, we can take the average of these. So, average stresses. So, bulk modulus is the ratio of average stress divided by volumetric strain. So, volumetric strain means change in volume upon original volume, average stress means sigma x plus sigma y plus sigma z divided by 3, we can get the average stress. Here the Poisson's ratio, it is very important and we have a certain ratio for this. So, let us say one object is this, when we stretched the object, its length varied from L to L plus delta L, length increased and diameter decreased. So, let us say decrement in the diameter is, initially it was sorry, it is wrongly placed. So, it is, let us say it was d, now it has been reduced to d minus delta d, and initially length was L, now it has been increased up to L plus delta L. So, there are two dimensions, longitudinal and lateral. Longitudinal means along the direction of application of force and lateral means perpendicular to the direction of application of force. Force is being applied in this direction. So, this direction is longitudinal and this direction is perpendicular to the force, it is the lateral direction. So, strains produced in the longitudinal and the lateral dimensions, the ratio of these two strains are known as the Poisson's ratio and it is fixed for different materials. So, here we can see the longitudinal strain is change in length upon original length and lateral strain is change in diameter upon original diameter. So, it is the ratio, this Poisson's ratio is lateral strain upon longitudinal strain. So, for most of the metals it lies between 0.33 and 0.25. Apart from this, this is the stress strain curve for mild steel. It is very important to understand this curve when we stretch any object in the UTM machine. So, this is the object which we try to pull in this direction, let us say for mild steel. Why for mild steel? Because these points are clearly defined for mild steel. So, we should understand कि if we stretch this object, let us say we stretch this object. So, how it behaves under different conditions of loading. So, if we see this O to A, this is the elastic point, if we release before A, it will come back to the original position. So, OH is the range where Hooke's law acts, OA is the elastic point, B is the upper yield point, C is the lower yield point, then D is the ultimate stress, ultimate point. So, where we can get the ultimate tensile strength and then sometimes here the neck formation starts. So, here it go like this. So, necking formation takes place and at this point it breaks. So, when we stretch this object, so it behaves like this and here we can see this is the modulus of resilience, the energy is stored up to the elastic limit per unit volume and this is the fracture point. So, here if we strike some object and it breaks, so that we get the toughness. So, the total energy is stored before the rupture of the object. So, we get this is the toughness. So, this was all about the simple stress and strain. So, here we can understand how different stresses, different strain works and subsequently in various lectures we will discuss more advancement of the strength of material. So, thank you listeners.